welcome back. 10.3, large sample hypothesis tests for a population proportion. So remember, we're dealing with p-hats and p's and percentages, okay? Proportions are percentages. Now that the basic concepts of hypothesis testing have been introduced, we are ready to consider how to use sample data to decide between a null and an alternative hypothesis. In a hypothesis test, there are two possible conclusions. We either reject H0, the null hypothesis, or we fail to reject it. The fundamental idea behind hypothesis testing procedures is this. We reject the null hypothesis if the observed sample is very unlikely to have occurred when the null hypothesis is true. Okay, so basically the idea is, look, if really 50% of the population exhibits some characteristic, and if we went out and took a random sample of 1,000 people, and our proportion was like, say, 60% that exhibited that characteristic, right? Is that enough evidence to suggest that, say, look, really, the true proportion is more than 50%? Okay, or did we just get back 60% as a result of sampling variation? Or was it just it just happened to be what we got from our sample? Is it more likely due to sampling variation, or is it more likely that the value we thought was true at the beginning isn't? And that's kind of the idea here. All right. So in this section, we consider testing hypotheses about a population proportion when the sample size n is large. As before, P denotes the proportion of individuals or objects in a specified population that possess a certain property. A random sample of n individuals or objects is selected from the population, and the sample proportion P hat is equal to the number in the sample that possess the property divided by the sample size n. This serves as the basis for testing hypotheses about P. Okay, so this is from our sample. This is the data gathered from the sample, and then we try to make some inferences or some judgments about the true population proportion. Okay, so based on what we got from our sample, can we make some judgments about what we think the true proportion of some population is? Okay, so in any event, the large sample test procedures is based on the same properties of the sampling distribution of p-hat that we used previously to obtain the confidence interval in Chapter 9. Okay, and this goes back to just Chapter 8 properties. Okay, mu of p-hat will equal the true proportion, and here's how we calculate the standard deviation for our sample proportions. Okay, and when n is large, the sampling distribution of p-hat is approximately normal, and again, that's typically when n is greater than or equal to 30. And the other property was that n times p greater than or equal to 10, and n times the quantity 1 minus p greater than or equal to 10. Not stuff we're going to have to worry about for these problems, okay? We're always going to assume that our population is large enough that we can apply this stuff in the examples we go through, so you're not going to have to worry about that, okay? And then here's our z-score formula, okay? Remember, in general, z is the sample value minus the true or assumed proportion. And then down here, we're dividing by our standard deviation. That was sigma p-hat, number 2 above. Okay, so that's just our typical z-score formula. Okay, and let's take a look at an example here. See how this stuff works, okay? So this is right out of the book, Impact on Food Labels. Understand the context. In June 2006, an Associated Press survey was conducted to investigate how people use the nutritional information provided on food package labels. Interviews were conducted with 1,003 randomly selected adult Americans, and each participant was asked a series of questions, including the following two. Question 1, when purchasing packaged foods, how often do you check the nutrition labeling on the package? Question 2, how often do you purchase foods that are bad for you even after you've checked the nutrition label? It was reported that 582 reported frequently to the question about checking labels, and 441 responded very often or somewhat often to the question about purchasing bad foods even after checking the label. Let's start by looking at the responses to the first question. Okay, based on the data, is it reasonable to conclude that a majority of adult Americans frequently check the nutrition labels when purchasing packaged foods? So here's our first kind of hypothesis test question. Okay, let's start by looking at the responses to the first question. It says, and then here's the actual question. Okay, based on the data, is it reasonable to conclude that a majority of adult Americans frequently check the labels? Okay, so P is going to be the actual proportion of adult Americans who frequently check labels. Okay, and so based on the wording underlined in green, here's how we set up our hypotheses statement. We start with what's called H sub 0. That's the value we assume to be the true proportion. And this is also the value that we're kind of testing against. Okay, I called the value we were asked to test against in the problem. Now, going back up to the question that's underlined up there, look, it says, is it reasonable to conclude that a majority, okay, that majority means what? Majority means more than half. Or another way to say that is what? More than 50% or 0.50. Okay, so in some problems we see, we're going to see the word majority, and what we need to realize is that just represents, look, are we, a majority is more than half. Okay, so basically, because they use that word, based on the data, is it reasonable to conclude that a majority of adults check the nutritional labels? That's what we're being asked to test. That's basically what we're being told to do. Find out if, based on this data that we got, do more than half of Americans check the labeling. So based on the conditions that you learned about for in 10.1 and 10.2, setting up your p-values, okay, H sub 0 is always going to be assumed to equal some number. So we're going to say, look, in this case, majority, we want to test if it's more than 50%. We're going to assume that the actual proportion equals 50%. So we go, all right, H sub 0 equals P, H sub 0 and P equals 0.5. And if you want, you can throw the 0 on the end there. I like 0.50 for 50%. And now, again, it says, can we conclude that a majority? That's what's giving us H sub A. So the alternative here is it really more than 50%? So we're going to see, is the proportion greater than 0.50? Okay. And again, that's what's in the type after that. The proportion of adult Americans who frequently check nutritional labels is greater than 0.5. That's basically what we're asking. Is it more than half? More than a majority? Okay. Or a majority. All right, so it'll get easier. This is usually the trickiest part, though, of the hypothesis process. I think is really looking at the question and figuring out what is the value that I'm testing against. When they say a majority, your H sub 0 is always going to be, well, we think that the true proportion is 50%. Majority means more than that, so then H sub A is going to be P greater than 0.50. Okay, so that's what we have to begin. So let me just clean this up. So basically, here's the process. All right, we were at H sub 0. We think that the proportion might be 50%, but the way the question was asked, do we think it might be really a majority based on our sample data? So we're going to test to see if the true proportion is actually greater than that. Okay. All right, so what do we need to do? Well, we need to look at our data. So what was our p hat value in this problem? Okay, well, of the 1,003 randomly selected Americans, 582 responded frequently to checking the labels. So in this problem, that's our p hat for question 1. It's that fraction, 582 out of the 1,003. All right, and we can round that as a decimal. Okay, let me come back down here with the work though. So look, p hat it's the number of people who exhibit the characteristic in the sample out of the total sample size. So again, in this case, 582 people frequently checked labels out of the 1,003 that were sampled. Okay. Now, what I'm going to do is I'm going to punch this in and round it to 2 decimal places. This is approximately 0.58. All right. So let's take a second to kind of digest what's going on here. We took a random sample of people. 1,003 people, we asked, did you check the labels before you buy the food? 582 said yes. So from our sample, about 58% of that sample said yes. So based on that, is it reasonable to conclude that more than half of the population in general checks the labels? Okay, and that's what we're looking at with this question. Say we took a sample, it came back 58%. Somebody decided to ask, hey, is it likely then that for all people that more than half, okay, does that apply to the population or just this sample? And that's exactly what we're looking to compute here, okay? And the way we do that is with these hypothesis tests. And so basically the idea now becomes this. Look, so we can assume that our sample proportions form a normal distribution, and we think that the true proportion who check the labels might be 50%. That's what we're testing. That's the number, that's H sub 0, that always goes in the center. Okay? And now we're basically asking, look, well then what would be the likelihood that we get a sample proportion of 58% or further if this is the case? All right? So this is the whole idea. If this is true, what is the likelihood my sample value would come back at 0.58 or further away from that value of 0.5 if it's true? So here's 0.58, a little up higher. And now what we're basically doing is looking for that shaded probability. Okay. If 50% is true, what's the likelihood that a random sample of 1,003 people would come back with a proportion of 58% or more? That's what we're looking for. And the idea is if this proportion is so low that it basically wouldn't likely occur, we say then look, this value is probably not correct, and we reject our null hypothesis in favor of the alternative. Okay, so let's take a look at how this works, all right, with these numbers here. So if 50% is true, what's the likelihood that our sample value would come back like it did or even further away from this value? Okay, is it due to sampling variability, or is it more likely the case that that assumed proportion of 50% is wrong? Okay, so let's figure it out. So what we now do is we look at the z-score. Okay. Okay, and if we want to do this out by hand, again, that's going to be p hat minus p over p1 minus p over n under the radical. All right, that's the formula from above. And again, you got to be real careful. You have to have your actual p, and you got to have your p hat value. Okay, and so this is going to be 0.58 minus 0.50, and make sure you're using the actual p 0.50 down here. And if you take a moment to punch that in, that basically comes out to the number 5. Okay, and I don't know if what you remember about z-scores, but being 5 standard deviations above the mean is extremely unlikely. Okay, if we actually take a quick look at a z-table here, right, it goes up to 3.49, so basically 3.5 standard deviations above the mean, and we're covering about 100% of the data by that point in time. So a z-score of like 3.5 would probably be like right here, right? And we've covered just about 100% of the data. So what's left to the right of it? No percent of the data. A z-score of 5 is going to be like way up here, and even less data would be past it. So again, we're getting a probability of basically 0 for this problem. So what does that mean? Okay. So here's where we put it all together, okay? If the true proportion of Americans who check the label is really 50%, a random sample of 1,003 Americans would have a sample proportion of 58% or more about 0% of the time. What does that mean? It just means it's incredibly unlikely to have happened. If this is true, we would almost never get a value like that or further away. Okay? And so this is the whole idea about accepting or rejecting the null hypothesis at this point. All right? So the rule is this to basically, the rule is this, okay? If the p-value is less than alpha, our significant level, we reject the null hypothesis in favor of the alternative hypothesis. So in any given problem, we're going to be given an alpha level, okay, or a significance level, if it's called, the probability of the type 1 error, okay, right, when we reject and we shouldn't have, okay. This is going to be given in any problem. So typically it's like set at 5%. If the likelihood that our sample data produces a value occurs less than 5% of the time, assuming this is true, we consider that a very small probability, enough to reject the null hypothesis. If it comes back greater than the alpha level, we attribute our results to just sampling variability. Oh, this is just due to the way our sample turned out. Not really a big deal. Okay, but to wrap up this problem, since our p-value is 0, that would be less than any given alpha level, whether it was 10, 5, 1%, or even 1/10 of 1%. A probability of 0 is going to be less than any alpha level. And so the conclusion is, well, the written conclusion is already there, but what we say is we reject H sub 0. Okay, we're rejecting the null hypothesis. You know what? We don't think that the true proportion is 50%. Based on our sample data, there's a lot of evidence here to suggest that it's greater than that. Okay, and that's the idea. So let's run through a couple more here. Definitions: a test statistic is a value computed using sample data. That's our p-hat. It is the value used to make the decision to reject or fail H sub 0. Okay, so we use our p-hat, and then we use that to calculate these probabilities, and then we decide whether to accept or reject. P-value is a measure of inconsistency between the hypothesized value for a population characteristic and the observed sample. It is the probability, assuming that H sub 0 is true, of obtaining a test statistic value at least as inconsistent with H sub 0 that was observed. That means at least as far away from H sub 0. So here's our normal distribution. We think that that's the value centered at H sub 0. Well, what's the likelihood? You know, the p-value is based on our sample value. If we get a sample proportion up here, we're calculating the p-value. Okay. The p-value also sometimes is called the observed significance level. All right, let's run through a couple more problems, see how this works. Plagiarism. Detecting plagiarism. Plagiarism is a growing concern among college and university faculty members, and many universities are now using software tools to detect student work that is not original. Researchers at an Australian university that introduced the use of plagiarism detection software in a number of courses surveyed 171 enrolled in those courses. In the survey, 58 of 171 indicated they believe that the use of plagiarism detection software unfairly targeted students. Okay, so this is going to be our sample proportion. We have a sample of 171 students, 58 of whom believe that the use of that software was unfairly targeting students. Assuming it is reasonable to regard the sample as representative of students at this university, does the sample provide convincing evidence that more than 1/3 of students at a university believe that the use of this software unfairly targets students? Okay, so this is what they're asking us about. Is there evidence that more than a third? That's telling us how to set up our hypothesis statement. Okay, so H0, okay, we're testing against 1/3 here. In fact, basically the words are almost giving your HA, your alternative hypothesis. More than 1/3. Is the true proportion greater than 1/3? Okay, which means that we're going to assume that the proportion is 1/3. All right, it's always the same number. That's what you saw in section 10.1 and 10.2. Okay, and H0 is always going to be P equals. H(a) is either going to be greater than, less than, or a not equal to the same value used in H(0). Okay, and again, that's just based on the wording. More than 1/3, that gave us P greater than 1/3. And I'm gonna use again decimals to two places here. So 1/3 rounds to about 0.33. Okay, so P equals 0.33 versus P greater than 0.33 here are our null and alternative hypotheses. Now, what is P hat? P hat is our sample proportion. That's our 58 out of 171. And when I punch that in, that rounded to about 0.34. So again, get the gist of this hypothesis test. Look, we took a sample of 171 students. 34% of them thought that this software was unfair. Based on that, isn't it reasonable to conclude that out of all the students at this school, more than a third of them think it's unfair, right? 34% is more than a third. The question could have asked, do more than 30% think it's unfair? A question could ask, do less than 35% think it's unfair, okay? So the numbers you see in blue are always based on the number we got in purple. If we get a sample of 34%, we can start asking questions. Is it likely that less than half? Is it likely that more than a quarter? Is it likely, in this case, more than a third exhibit this trait? And that just happens to be the value that this question's using, is 1/3, okay? Because the sample came back a little bigger than that. All right. Now, again, there's no significance level given in this problem, so I'm going to say let's use 5%. That's a pretty common significance level. So what that means is, look, we're going to calculate the likelihood that if the true proportion was a third, what's the likelihood we would get 34% back or more in our random sample? And if that probability is less than that 5%, that's going to be low enough to reject our null hypothesis, get rid of that in favor of this. That's what we call convincing evidence. Okay, so again, in terms of the diagram, we assume normal distribution for our sample proportions. We think the true proportion might be 1/3. What's the likelihood we got 34% or more, right, greater than that, back? And the thing you got to be careful is, look, even though this has greater than 0.3, we're not shading to the right of 0.33. That's not what we're doing here, okay? We're always going to cut it off at our p-hat value and then shade in the same direction as the inequality in the hypothesis statement. That's what's going on here. Okay, if the true proportion is 33%, what's the likelihood I would get a sample value of this or further away back? That's what we're going for. Okay, and again, if that's less than the significance level, we reject H(0). If it's not, we accept. Let's see how this one plays out. So again, in terms of the math, let's see, the z-score would be sample minus hypothesized over standard deviation using hypothesized. And what was the sample size? 171. And we get a z-score of about 0.28 back. Okay, that's not too far away in terms of standard deviations. That's a little more than a quarter standard deviation above the mean. The associated p-value, if we again go back to our z table here, okay, 0.28, 0.28 is, so the area to the left is 0.6103, We want the area to the right, so that's 1 minus, and that's going to be 0.3897, right? So what does that mean? What does that mean? Okay, here it's that. I just wrote that. So the p-value, 61% was to the left of that. So 1 minus gave me about 39% of the time for that region. What does that mean? Well, if 33% is the actual proportion of students at this university who feel that this software is unfair, a random sample of 171 students from this university would have a sample proportion who think it's unfair of 34% or more, almost 39% of the time. That's not that unlikely to occur. This is certainly greater than our 5% significance level. And so what we really say is, look, we attribute our sample value to nothing more than sampling variation. This is not really an unlikely result to get if this is the true value. Okay? Since our p-value is greater than alpha, we fail to reject H sub 0. There is not convincing evidence to suggest the true proportion of students at this university feel the software unfairly targets students. And again, that's like our written conclusion here. But mathematically, we come up with the z-score, we come up with the associated p-value, we compare it to alpha, and we go from there. Okay? We go from there. Now, from here, I'll show you how to do it on the calculator. Okay? Because, you know, this isn't too bad, but it can be done very, very quickly on the calculator. Okay? So coming back up here, let me make a little more room. Get rid of this so I can show you how to punch it in. All right. And nothing's going to change in terms of our conclusions, but you know. All right, so on the calculator, what we are going to do is you're going to go to Stat. Okay, go to the Stat button, go to the right twice to the word Tests. And for this stuff, we are looking at number 5, a 1 proportion z test. Okay, we have a single proportion, 1 p-hat value, and we always use z for this stuff. So this is how we do hypothesis tests for single proportions on the calculator. So if you bring that up, what you'll see is the following. You're going to see p sub 0. That is our h sub 0 p-value. Okay, then you're going to see x and n, similar to what you saw with the hypothesis, the confidence intervals, excuse me. So x is the number out of the sample that exhibit a characteristic, n is the sample size. Then you're going to see proportion. Now basically these are the 3 ways that we can set up our h sub a, if you will. There's an option to do a not equals p0, there's a less than p0, there's a greater than p0. Then below that, you see calculate, draw. Okay, so for this particular problem, here's how it's going to look. P0 is our null hypothesis value, that's 0.5. X is the number that exhibit the trait. That was the actual 582 here. N is the sample size. That is 1003. Now, for which one of these tests we want to run, well, just look at H sub A. We want to test greater than P sub 0. So we're going to highlight this one. So you just use your arrow to highlight that and hit enter. You should see that it's highlight. Now you can do calculate or draw. I always do calculate. It just gives you a little more information. Draw kind of gives you information, but it also shows you like the normal distribution curve and shades the region that you're looking for. You can feel free to use that if you want. You don't need to, whatever. Okay, now when I do calculate, here's what I see. I see at the top, proportion of time greater than 0.5. Okay, then I see z equals 5.08 dot 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 dot. Below that I see p equals 1.85 such and such e negative 7. And our p hat value is also given. Notice that's 0.58. 0 dot dot dot. That's pretty close to what our approximation was, okay? And it shows you your sample size once again. Here's what we're interested in, these two guys right here. There's your z-score, okay? Notice it's basically what we got when we ran it by hand. It's a little bit more accurate than ours because we rounded this to 0.58, okay? The calculator does a little bit better of a job of doing that. So there's a more accurate z-score. And then here's the p-value. Now notice that scientific notation with that e negative 7. That's 1.85 times 10 to the negative 7th. So we're going to move this decimal 7 spots to the left. We'll see 1, 2, 3, 4, 5, 6, 7. Fill in with zeros. Right? That's a tiny little number. That's 0. There's the same p-value of 0. Okay, so just remember scientific notation. You're basically looking at 0. So we're getting back more or less the same information. We did it by hand. P was 0, less than any alpha level could possibly be. So again, we reject. All right. Looking at this next one on the calculator here. So again, we're going to go stat tests, and number 5. Okay. Okay, so for P0 for this, we used 0.3. Now here we can actually do 1 over 3. Again, make it a little more accurate. So I'm going to punch that in. X and N. Let's see. X were the number 58 out of the 171 that thought it was unfair. And in terms of our alternative hypothesis, again, we tested greater than P sub 0. And now I'll calculate, and I'm getting z to be about 0.16 and a p-value below that of a 0.44. Okay, so again, a little more accurate than ours because, again, we rounded. I used 0.33 for a third, and I used 0.34 for that. But very similar data coming back. Okay, z-scores are pretty close to each other, and the probabilities aren't all that far apart. And in terms of the overall final answer to the problem, right, 44%, 38%, both of those are greater than 5%. So we fail to reject the null hypothesis. Okay, so I'd recommend doing it on the calculator. It's a lot quicker and it's even a bit more accurate, especially if we start rounding to 2 places or something. Okay, now look, as illustrated in the previous examples, in 10.8, we got a really small p-value. So a small p-value indicate that the sample results are inconsistent with our null hypothesis, just meaning very unlikely to occur. Whereas larger p-values, like the one we got in 10.9, that 39%, are interpreted as meaning the data are pretty consistent and that sampling variability alone is a plausible explanation for what was observed in the sample. As you probably noticed, the 2 cases examined, p of about 0 and p of about 0.3897, were such that a decision between rejecting or not was clear-cut. A decision in other cases might not be so obvious. For example, what if the sample had resulted in a p-value of 0.04? Is this unusual enough to warrant rejection of H sub 0? Right? That's just a little less than 5% of the time. It could still happen. How small must the p-value be before H0 should be rejected? To answer these questions really depend on the significance level alpha, the probability of a type 1 error selected for the test. For example, suppose that we set alpha to 5%. This implies that the probability of rejecting a true null hypothesis is 5%. 5% of the time we'd be wrong is what that means. To obtain a test procedure with this probability of a type 1 error, we would reject the null hypothesis if the sample result is among the most unusual 5% of all samples when the null hypothesis is true. We would reject the null hypothesis if the computed p-value was less than or equal to 5%. If we had selected alpha at 1%, H sub 0 would be rejected only if we observed a sample result so extreme that it would be among the most unusual 1% of the time if the null hypothesis was true. A decision to reject or fail to reject the null hypothesis results from comparing p-values to the chosen alpha or significance level. We reject if the p-value is less than or equal to the alpha level, otherwise we fail to reject. Okay, now as far as you guys are concerned, you don't have to come up with the alpha levels on your own. It really, that's more nitty-gritty stuff that comes down to really what is it that we're talking about. In the medical field, it's not uncommon to have an alpha level that's really small, like 0.0001. If we're testing new drugs and the side effects of those drugs, we don't want that to occur very often. So we want to have significance levels that are really small to avoid certain types of errors. But ultimately, for what you guys are going to be doing with these, they will be given in the problem. Your job is to know this, okay? Based on our p-value, will we reject or fail to reject the null hypothesis, okay? Okay, look at next problem here, 1010, water conservation. Suppose that in December of 2014, countywide water conservation campaign was conducted in a particular county. In January of 2015, a random sample of 500 homes is selected, and the water usage is recorded for each home in the sample. The county supervisors wanted to know whether the data supported the claim that fewer than half the households in the county reduced water consumption. The relevant hypotheses are, and we're going to set these up. Now, suppose, again, we have a sample size of 500, and suppose that we found out in our sample of 500 that 44% of the households reduced their water consumption. Certainly in our sample, that's less than half. That's less than 50% of the houses, right? So based on our random sample of 500 coming back at 44%, and again, I'm throwing that number on there because we need a number that wasn't given. Okay. So if a random sample of 500 households shows that 44% have reduced water consumption, is that enough evidence to suggest that of all the houses in the county, less than half have? Or is this 44% just due to sampling variability? That's what we're looking at here. Okay, so we're going to set up a hypothesis test. H sub 0, H sub A. We think the true proportion might be this versus less than, greater than, or not equal to. So going back to the words, the county supervisors wanted to know whether the data supported the claim that fewer than half. So that's our alternative hypothesis. Is the proportion less than half, less than 0.5? So we're going to assume the true proportion is 0.5. Okay? Now, I'm telling us our p-hat value here was 44%. Okay? And our sample size is 500. So let's go into stat tests. And number 5. Okay. So under the 1 proportion z test, p sub 0 is 0.5. X, again, careful, is the number out of our sample that exhibited the trait. Well, we know that's 44%, so we need 44% of our sample. So you can actually just punch it in like this, 0.44 of the 500. Okay, and when you do that and hit enter to go down to n, it'll change that to the actual value of 220 right in the calculator for you. And n, again, is 500 here. And now be careful which one we're picking up. The alternative hypothesis this time was less than. So I'm going to do less than p sub 0 is the one I'm going to pick. And you should be picking that as well. And then go down to calculate and let's see what we get. So we get, again, a big old z-score of about 5.06 and a p-value of 0.9999, right? That's basically 100%. Okay. All right. Now let's see here. Oh, whoops. I must have forgot to change my point P0 to begin with. I never actually punched that in, so ignore my numbers. Ignore the numbers I just said. I got to run through this again real quick. Standard procedure for Mr. Rosenberg sometimes, guys. You know that. P0, 0.5. I'm just repunching this in. 0.5, 220, 500. Now I'll calculate. There we go. And here's the numbers that I was expecting to see. Those were off. Okay. Actual value, Z, negative 2.68-ish with a p-value of about 0.0036. There we go. Again, my error was I didn't change that. That was a big no-no. In any event, okay, look, we got a very, very small p-value back. Again, I'm going to say alpha is 0.05. And you're going to use alpha as 0.05 unless you're told otherwise in any problem. That is to be assumed. That's the most common significance level used, okay? So assume 0.05 in a problem unless you're told otherwise. Sometimes it'll be like 0.01 or something else, okay? So just be careful. And on the WebAssign problems, it's very clear in each problem, okay? But in any event, let's draw our conclusion. Look, this is certainly less, our p-value, we compare p to alpha. That's less than 5%, right? In fact, that's less than 1% of the time. 0.003 is really a very small percentage of the time. All right, so again, let's make sense of what's going on. We thought that the true proportion was 50%. Our sample came back 44%. What's the likelihood we get that or something further away with a sample of 500? And what we came up with is that percentage of time that would occur, less than 1% of the time. That's very, very, very unlikely of an occurrence then. It's very unlikely we would get a sample of 0.44 or further away if the true proportion was 50%. Okay, so what's the conclusion? Since p-value is less than alpha, reject the null hypothesis. Okay, there is evidence to suggest that less than half, right, we're accepting this, in this case, that less than half of the county residents have reduced water consumption. Okay, that's the question. The county supervisors want to know whether the data support the claim that fewer than half the households reduce the water consumption. Yes, the data does confirm that. Right? It seems to be the case that less than half have reduced. Okay, a couple more examples to go here, and hopefully get the gist. Unfit teens, the article, 7 million U.S. teens would flunk treadmill tests, summarized the results of a study in which 2,205 adolescents aged 12 to 19 took a cardiovascular treadmill test. The researchers conducting the study indicated that the sample was selected in such a way that it could be regarded as representative of adolescents nationwide. Of the 2,205 adolescents tested, 750 showed a low level of cardiovascular fitness. Does this sample provide support for the claim that more than 30% of adolescents have a low level of cardiovascular fitness? We answer this question by following, don't worry about the 9 steps, that's how the text does it. We'll just worry about following the steps I showed you. For carrying out a hypothesis test, we will use a 5% significance level. Okay, so typically that's given, and there it is at 5% again. Okay, so what's the question? Does the sample provide support for the claim that more than 30%? Is the proportion more than 30? So we're going to assume the proportion is 30 for H sub 0. Now, our p hat value is the proportion out of in the sample. So of the 2205 selected, 750 showed a low level of fitness. Okay. So in terms of the calculator, okay, again, if you want, set up your diagram. And if you want, just to get an idea, what does this even equal? What is that? 750 out of 2205. It's about 34%. Okay, so that's certainly more than 30%. And again, another relevant question could have been, does it support the claim that more than a third? We could have tested that. 34% is more than a third, like we saw previously. So again, the hypothesis test setup is always just something relevant to what our p-hat value was. Here we got 34%, so we're wondering, hey, is it likely then that in general more than 30% of the population is unfit? Well, let's figure it out. Okay. So again, just if you want the visual, you don't really need these. We're assuming 30. What's the likelihood? We're going greater than, so we're going to shade to the right of our p-hat value, and we're finding that probability right there. Okay, so stat tests, number 5, P0 was the 0.3. X is the number, that's 750 here. N is the sample size, 2205. And in terms of the test, we're going greater than again. You just look right back here. Greater than is what we're going to select and calculate. I'm getting a z-score of about 4.11. Again, very, very high, with a associated p-value of basically 0. I see that scientific notation, 1956 E -5. So that's 0. And you know what? That's certainly less than 5%, our significance level. So we are going to reject the null hypothesis. In favor of the alternative, there is evidence suggesting more than 30% of teens are unfit. You know what? I bet more than 30% of 40-plus-something-year-old math teachers are unfit too. So maybe we go out and run or something. I don't know. All right, one more example. College attendance. The report, California's education skills gap. Modest improvements could yield big gains. States that nationwide, 61% of high school graduates go on to attend 2-year or 4-year colleges after the year after graduation. The college going rate for high school graduates in California was estimated to be 55%. Suppose that the estimate of 55% was based on a random sample of 1,500 California high school graduates in 2009. Can we reasonably conclude the proportion of California high school graduates in 2009 who attended college the year after graduation is different from the national figure? Set up a testing procedure for hypothesis tests with a significance level of 1% to answer the question. Okay, so again, we're given the alpha level, and look at the way the question's asked, okay? Is there evidence, can we reasonably conclude that the proportion of California graduates who attend college the year after graduate is different from the national figure? Okay. We're testing against the national figure. That's the 61%. But think about how we're going to set up the alternative hypothesis here. It doesn't say is it less than the national figure. That would be p less than 0.61. It doesn't say is it greater than the national figure. That would be greater than 0.61. It says is it different. Here's a case where we're using the not equals. So we're going to assume the California rate is the same as the national figure, and we're going to test to see if it's different. Okay. P hat is the 55%, the college going rate in California, and that's the value we're using for p hat here. And our sample size was 1,500. Okay, suppose that the estimate of 55% was based on this random sample. So there's our p hat value, out of that sample. Okay. Now visually, in terms of the diagram, what we're looking at here, this is called a two-tailed test. Everything we've done so far is called a one-tail test. We're finding the area in one tail of our normal distribution, okay, whether the left side or the right side. When a not equals case, here's what this diagram looks like. Null hypothesis, 0.61. What's the likelihood a random sample will come back at 0.55 or further away? Well, that gives us this side, but it also gives us symmetrically this side as well. So we're not only asking, what's the likelihood, we're basically asking, what's the likelihood it was more than this distance away in either direction? Okay, so we're basically going to have, these two regions, but we don't have to work hard to get those. I mean, it's symmetric. If we can get the area of that region, we multiply it by 2. And you got to do that if you're using your z table. But if you're using the calculator, you're going to punch, the appropriate p sub 0 in, and it's going to do it for you. Okay, but that's basically what we're looking at. And look, how far away is 0.55 from 0.61? 0.06. So if I add, that would take me to 0.67. Look, and again, I'm going a little deeper into this than I need to, and that you need to worry about, but we're basically asking for a not equal situation, okay? We can have one value. What's the likelihood it came back that far away or further in that direction, or symmetrically off in the other direction? And that's what's called a two-tailed test, right? We don't ever need that extra value of 0.67 to do this. Okay, we just have to have an understanding of, this is what it means to be a two-tailed test, and that's the not equals. Okay, so watch. Look, we're going to go stat. We're going to go test number 5. P0 is our 0.61. X, again, is the number that exhibit. Now, N is 1,500, and we want 55% of that. So again, you can punch it in just like that. Just make sure you're doing that and not just putting the 0.55 in. That's not going to get it done. Okay. And by the way, that ends up being 125. And then for the proportion down below, we're going to pick up the not equals p sub 0 one this time. And not equals, and calculate, and again we're getting a z-score that's incredibly low, a p-value with an e at the end of it, so that's basically 0, which is less than our significance level of 1%. And once again, because it's less than, we reject the null hypothesis in favor of the alternative. It is likely the college going rate for California students is something other than the national figure. Okay, and there you go. All right, so stay tuned. We'll be doing more of this with sample means next. Basically the same idea, just different buttons to push, and instead of z-scores, t-scores. Okay, I hope you guys have a great day, and let me know if you have any questions. See you.